So we collected our data, we ran our statistical test, and let's say that we get a very small p-value, and therefore we are rejecting the null hypothesis. What does that really mean? Well, rejecting the null hypothesis means that we are confident that there is an effect. For example, that the difference between two groups is different from zero. There is an actual difference between them in the population. But it does not tell us how large the effect is. It's just telling us there is an effect, nothing about the magnitude of the effect. It doesn't tell us whether that effect is actually important or useful or relevant to our study. There's nothing about it. It's only there is something. Whether that's relevant or not depends on you. It only says that the data, what we collected, is unlikely under the null hypothesis. That's it. There's nothing more to it. Your data, if you are assuming the null hypothesis, is unlikely. Maybe it's also unlikely under the alternative hypothesis. That's something we never think about. Maybe it's just that the data are unlikely. Maybe we were just unlucky in the sampling process, and the data we have, it's special in some sense and doesn't really represent the populations. So the fact that we reject the null hypothesis doesn't mean that we should go and accept the alternative hypothesis. Maybe it's also unlikely under the alternative. So what I'm trying to say here is that in the p-value, we are actually conflating many different aspects of our data and our hypothesis. And at some point, we have to start talking about the practical significance, not so much the statistical significance of a result, but the practical significance. Why? Because with large samples, we are more likely to obtain a small p-value. We saw about it. The larger the sample size, the smaller the p-value, because the random error is reduced. We have less variation in the sample means. Standard error is lower. That's it. Now, at some point, this means we will eventually achieve statistical significance. It's just a matter of increasing the sample size more and more and more and more. Now, this is, of course, if the null hypothesis is incorrect. And the thing is, we are comparing the p-value with a threshold, with a significance level. Normally, alpha equals 5% or 1%. But this is completely arbitrary. Why 1%? Why 5%? Actually, the story of why we're using 5% is quite funny. It's because Ronald Fisher, the person who kind of started this whole thing of statistical significance, illustrating an example in a book, said, okay, if we are 2 standard deviations away from the mean in a Gaussian distribution, that leaves a probability of about 5% in the tails of the distribution. So that looks like something easy to remember, easy to illustrate. Let's just use that as an example. And that's the only reason why we're using the 5%. But the point is, any threshold, any alpha is completely arbitrary. The true effect, the true magnitude of the effect in the population, it is what it is. It doesn't depend on us. It doesn't depend on the sample. It doesn't depend on the sample size. It doesn't depend on P. It doesn't depend on alpha or our hypothesis about it. It is what it is. And so what we should do is focus more on the magnitude on the effects. So not so much on saying whether there is an effect or not, but how large is it? Not testing whether it exists, but testing how large it is. So next to a p-value, we should always report our estimate. So we are estimating a quantity, a population mean, for example. Give me the estimate. So essentially, what is the mu hat, sample mean? And then we should put next to it some kind of quantification of the random error. So a confidence interval, standard error, things like that. The problem with the p-value is that it conflates both of them. It conflates the estimate of the effect and the uncertainty of the effect. So if you think about the t-score from which we compute the p-value, we had the sample mean minus mu over sigma and sample size square root. So the numerator, it's telling us about the magnitude of the effect. The denominator is telling us about the uncertainty in that estimation. And actually, you see, this is precisely the standard error of the mean. And so the p-value is computed from both. We could have a very small p-value because we have a very large effect, or because we have a very small random error. It's conflated, both of them. What really matters for us in a practical sense is this. What is the actual effect? What is mu? And so we should try and always report both of them separately, not just the p-value, but a quantification of uncertainty, random error, confidence interval, something like that, and an estimation of the actual effect. So we know there is a certain degree of random error when we use the sample mean to estimate the population mean, right? Now, this is just like any other statistic, not just the sample mean. Anytime we're trying to estimate something about a population from a sample. So we could compute confidence intervals to quantify random error. How they're computed is as follows. So we say the estimation for mu is the sample mean plus minus a z-score times the standard error of the mean. And what is this z? Well, it's a number that depends on the confidence level we want to have. For example, if we want a confidence interval at the 95% level, then this z-score is going to be approximately 1.96. Again, this is all based on models, it's based on assumptions, but it just gives us a rough intuition, a rough estimate of how much variation we expect. And so if we compute this from our example, what we have is that now our estimate of A is not just the sample mean. It's going to be the sample mean plus minus a certain random error. And we say that in this case, the confidence interval, if we compute it, is anywhere between basically 5 or 6. For treatment B, we have anywhere between 5.06 and 6.25. And for C, it's anywhere between 5.78 and 6.62. And what we notice is that all intervals overlap. Now, what's really happening in the confidence interval? Let me show you here the example with treatment B. So we have a histogram of the actual observations we get in our study. And from those observations, we have our estimate of mu B, just under 6. Then in red over here, we have the sampling distribution that we are estimating, given the variation we observe in the sample, given the sample size, and given the estimation again of the true score. So in red here, we have our estimation of the sampling distribution. And what we are doing with the confidence interval is give the extremes of this portion over here that contains 95% of the density in that distribution. So what this is telling us is that over here we leave 2.5%, and over there we also leave 2.5%. So what is the central 95% of the distribution? What are the boundaries that contain 95% of the sampling distribution? And this gives us an idea of how much variation we should expect. So what this really means, technically speaking, is if we replicated the experiment and we collected more and more and more samples, then computing the confidence intervals given those samples, 95% of those intervals would contain the true mean in the population. So 95% of the intervals will contain or are expected to contain the true mu B. And so what this is telling us is that the three intervals overlap a lot. So we are not really certain that if we account for the random variation due to sampling, we really observe differences between them. So it's always a good idea to compute the confidence interval as a very nice way to report the amount of variation we expect due to sampling. And then we also have to wonder, is the null hypothesis false anyway? Because almost always there is a true difference. There is a true effect, maybe too small. And that's the only thing. It's too small to detect with a small sample. So again, if we think about it, the null hypothesis says something like mu equals 0, or the difference between two treatments equals 0. So it could be something like the mu for A equals the mu for B. So the difference is exactly 0. Now, well, in many cases, this is going to be completely unreasonable. It's going to be different from 0, of course, but just very close to it, so close to it that it doesn't make any difference in practical terms, that the difference is irrelevant. And so in practice, if you think about it, we don't really make type 1 and type 2 errors. The null hypothesis is in many cases false almost by definition. These two treatments are not exactly the same. They are just a tiny little bit different. So forget about type 1 and type 2 errors. What we should really care about are what some people call the type S and type M errors. So a type S for sign or type M for magnitude, meaning we maybe get the sign of the difference wrong in the sense that we say A is better when in reality it's the other way around, B is better, or a magnitude. Maybe we say that it's 3 units better, but it's actually 5 or 2 or 10. And that's actually what we should care about, not whether there is an effect. Pretty much always there is an effect. The point is in which direction and how big the effect is. It's not just about the existence of the effect. So we have to consider all the time how much power we want to have, how likely we want to be to detect the effect sizes. Because again, it's not just about there is or there is not. If that's how we're thinking, we have to worry about statistical power. There is an effect, and then we start quantifying how large it is. We have to worry about the effect sizes, not just the p-values. So, for example, if you ask me if we're testing hypothesis about correlation of 0, this is completely absurd. So what we are testing here is that the data are completely random. Two numerical variables are completely independent from each other. That's never going to happen. In our data, there's always going to be some tiny, small correlation. It's going to be very, 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 very close to 0. We might have a lot of data and test for it and maybe figure out that the correlation is 0.00002. And we are very confident that it's 0.0002 plus minus a tiny bit of error. But what's the point? This is completely irrelevant. This is random for all practical purposes. And so, again, think about it. The null hypothesis, most likely than not, it is false by definition. We have to worry about the direction of our claims and the magnitude of our claims. And all this very much relates to the significance level and power. So again, the type 1 error is one in which we incorrectly reject the null hypothesis. We conclude there is something where there isn't. It depends on the significance level, because we have to observe a p less than alpha, and this is typically the one we care about. But there's also the type 2 error, the one in which we fail to reject the null hypothesis and conclude there is no effect when in reality there is one. And this mostly depends on the sample size. It also depends on the effect and the variance in the population. We've seen that, but the thing that we can control, the only thing that depends on us, is the sample size n. And this is what we should care about more often, because if we fail to reject the null hypothesis, that doesn't mean that we accept it. That only means we do not have enough evidence, normally that means enough data, to be sure that the null hypothesis is false. So it's never about accepting the null, it's about failing to reject the null. We do not have enough data for it. And what we see is that in many cases, people forget about this type 2 error. They collect the data, they run the test, we get a p-value larger than alpha, then we conclude there is no effect. Well, maybe there is. Maybe you just didn't have enough data. That is the point. And so something we should always be careful about, and we should keep in mind at all times, is statistical power. And there is this tool here, G-Power, that I really encourage you to take a look at. It's going to allow you to make certain computations, certain calculations about what is the required sample size for you to test a certain effect of a certain magnitude. Or if you already collected the data, you can plug the numbers in there saying what is the observed variance, how much data you have, what kind of test you're running, what is your hypothesis, and then it will tell you how much statistical power you had in your experiment. So very often we're going to see that we have a negative result, the p-value is larger than alpha, we had bad luck, but maybe it's all about the power. Maybe your test is not powerful enough. So you could run a different test if it follows the assumptions, or if the data follow the assumptions, or you could collect more data. And then at some point, it's going to tell you, you do not have statistical power, but your sample size is already huge. So it tells you the effect has to be smaller than a certain amount because you're still not detecting it. And then at some point you say, okay, I'm going to stop. There is no effect, or the effect is so small that we are still not observing it with this huge amount of data. We can stop and accept the point that there is no effect. So always keep in mind this statistical power. It's not that there is no effect, it's that we do not have enough evidence, enough data to detect the effect. And going back to this question that we were asking a few videos back, what is an appropriate size? In reference to this notion that usually 30 points are enough. So first we have to know how much variation there is in the data. That's a property of the population. Again, we do not have any control over it. We have to figure it out. We have to estimate it somehow, either look in the literature or run a pilot study in which we can have a rough estimate. And then we have n, the sample size. It should be as large as it would take for the test to detect an effect of a certain size with a certain probability. So if we run the numbers, what we have is something like the following. Let's say that we estimate from previous data or a previous study or the literature that sigma is 1.4. So the standard deviation of the population is 1.4. That's the amount of variation we have in the variable. And let's say that we want to detect an effect of at least 0.3 units. So something that is larger than 0.3. Anything smaller than that, we don't care. So this is somehow telling us what is the practical relevance of the effect. It has to be something larger than 0.3. And then we want to be able to detect it 80% of the time. So with an 80% probability, we want to be able to detect it if we run a study. So that means a beta of 0.2. Assuming a 5% probability of a type 1 error. So assuming that 5% of the times we will incorrectly reject a null hypothesis. So significance level equal 5%. Then we run the numbers and it tells us the sample size we need is actually 343 observations. So we need 343 observations if we want to be able to detect an effect of at least 0.3 with 80% probability, knowing or willing to take a probability of 5% that we make an incorrect claim, given a population that has a variation of 1.4. And this is actually the real answer to our question. How much data do we need? Well, it depends. It depends on the properties of the data. It depends on what kind of effect you want to detect. And it depends on how likely is it that you want to be incorrect. And it further depends on the test. It depends on whether we run a t-test or a Wilcoxon test. They have different equations to run, and we might get a slightly different number. It depends on the assumptions of the test. It depends on the alternative hypothesis. I'm not going to get into details here, but the point I'm trying to make is the answer to this question is always, it depends on the properties of the data, and it depends on what you want to detect, and then how willing are you to make a type 1 or type 2 error. Then you get the answer. And still, in that case, remember that we only get one sample. So we have one sample of 343. Given that one sample, we have no idea about the population. What we have is one sample that we hope to be representative, and from there infer something about the population. But maybe we just got a bad sample. We don't know. And so at some point, we have to think about the difference between a result being significant or relevant or interesting. Let me illustrate just, drawing a Venn diagram. So let's say here in blue, we have all possible studies we could think of in our field. Then some of them are going to be interesting. And some of those will be actually relevant to our field. Those that people will actually go around and read and start using because those are relevant to the others in your field. Now, the point is that statistical significance is not something that is here within the green bubble. It's something that overlaps. So we have over here in orange the statistically significant studies, those for which we were able to achieve a statistical significance, a small p-value. And what you should realize in here is that the fact that you get a statistically significant result, that doesn't mean that you get a relevant result. That only means that you are certain there is something. Whether that something is relevant or not, it's not for me to judge. But it's not for the p-value to judge either. So in principle, we would really like to be over here, get a statistically significant result that is relevant. But maybe what we get is a statistically significant result that it's over here, something that, yeah, it's positive, but it's completely irrelevant. And even more, we have to realize that if we get a negative result, then maybe we are over here. The fact that we get a large p-value doesn't mean that what we're looking for is not relevant or doesn't exist. It just means we don't have enough data to be able to claim that. Or of course, we might be over here. You don't have enough data, but you know what? Actually, there's nothing, or it's completely irrelevant. And so be very careful when you're looking at p-values into thinking that if you have a small p-value, that means you have something relevant. And if you don't have a p-value, it's either irrelevant or non-existent. That's not what the p-value is measuring.